As part of a digital twin or smart refinery initiative, one of the key things to have is essentially intelligent drawings, namely PNIDs, since they are the main documents that describe the process within the facility. And for that, we'll be showing the platform shown on the screen for intelligent PNIDs. What the platform does essentially is grab your existing AutoCAD files and moves the information from those drawings into a database structure for you to visualize the drawings as I'm showing you on the screen. And what does it mean to have an intelligent drawing? It basically means one of two things: that you can either extract information from the drawings or you can link information to the diagrams. Starting from the perspective of extracting information from the drawings, once the drawings are processed inside of the platform, one of the things that happens is that all of the content across the PNIDs get indexed. This gives you a clear-cut picture of all of the different components that exist on the PNIDs. So for instance, if you want to understand how many discrete field-mounted instruments or how many reducers exist on any particular drawing, you would have the ability to understand those inventories. One way that we describe these inventories is as takeoffs. And this is an example of a takeoff from a customer that had about 250 PNIDs. And this is the result of everything that we were able to extract. The key thing about these inventories extraction is that then you're able to do mass associations for the drawing set. So if you need to understand what's your instrumentation inventory or relief device inventory and confirm these across other sources, this is going to be the foundational key point in order to understand that information. Now, once we have categorized all of the objects on the drawing, what remains essentially are the lines in the background. So in order to handle the lines, we basically define process lines within the tool. These process lines that, if I highlight them at once, it kind of looks like a Christmas tree, is actually very straightforward. Each line is defined from its origin in green to its destination in orange, and the path is in blue with everything in between. This gives the platform the understanding of all of the different components that exist on the line, as well as the direction of the process flow of that particular path from source to destination. Now, why is this useful? Two main features. The first is the fact that you will understand, as part of those inventories that I showed prior, all of the different contents of the line. But at the same time, it allows you within the software to basically search for any tag name across what we call our distillation tool. And if a particular process line exists across more than one drawing, there's a lining path existing across 3 particular PNIDs, it will give you the ability to visualize that entire path across however many drawings they occur. This happens to be extremely relevant and important, especially when trying to conduct, let's say, lockout tagouts or de-energization routines. It just gives the users a very clear-cut understanding of what the path is of that line to get to the block points necessary to execute the activities that have to be executed. And that kind of sets the foundation in terms of the information that, from a structural perspective and a visual perspective, can be understood from the diagrams. That takes us to the next level of data extraction, which is data extraction, but in a bit more of a structured fashion. For this, we use a tool that we call the hierarchy. This hierarchy allows us to build multiple types of hierarchies within the software. One of the key hierarchies being hierarchies tailored for predictive analytics. And this right here is an example of such a hierarchy for the vessel V1001, which is the vessel that you're seeing in the center of the screen. You can see that it parameterizes the variables that you would require for a predictive analytics model, and it allows the user to basically select the instruments that are associated to each of those variables of the equipment. So by the end of the creation of the hierarchy, you have a direct association of the instruments that are measuring the parameters of interest for the predictive analytics, basically allowing predictive analytics implementations to be a lot faster with direct input from users in the field. And this closes the loop on the multiple ways in which data can be extracted from the drawings. As mentioned before, aside from data extraction, another key thing of the intelligent drawings is data linking with the diagrams themselves. And we have a number of examples to show this. One of the main reasons for association or linking is with document control systems for MOCs. As you would have imagined, in the platform, we do have the ability to basically portray red lines on the drawings. This way, inspectors or maintenance personnel can portray the red lines directly on a tablet in the field, and these then can, once created, automatically be notified of the drafting team so that the MOC process can be kicked off for these changes to be executed on the master CAD files. That's just one of the main things of why you want to link the intelligent drawings, in this case, to your document control system for streamlining of MOCs for the drawings. Aside from this, one of the key features that our customers utilize quite a bit for visualization purposes and subsequent linking is basically the definition of circuits or systems on the drawings. This is an example of a piping circuit for inspection purposes. And if I focus on one of these specific circuits, you can see that I've got the label for it right here on the PNID. I'm able to basically click on that label and get to the isometric drawing that is associated with this particular piping circuit. And here we have another example of data association, in this case to an inspection data management system, which could be GE's, APM, or any other product. You can see that each of the thickness measuring points are associated with the external data source, so I can visualize, for example, the remaining life on those points, the actual thicknesses that were taken at each of the CMLs, and if I want to see further data, I can just click on the actual CML point and I can visualize even a chart of how the thickness has behaved over time. This is again a linkage to an external source. It's not information that's being stored within the platform itself. So this is a second use case in terms of linking to actual IDMS information. A third use case is one for linking with 3D models, and this can be photogrammetric or geometric. In this example, we have a photogrammetric model in which, once the drawings have been processed, it actually indexes all content. So I can, for instance, search for a very specific drawing equipment ID, let's say, for instance, F1500. And when I click on that, it's going to show me within the map of the facility where the asset is located. It's going to bring me to the 3D model that has that asset representation, so I can kind of walk around this particular area and visualize how the asset looks like and get a dimensional understanding of it. It'll also index the intelligent drawing that has the label of the equipment. So if you're doing an activity such as a lockout tagout, you can have the 3D model next to the 2D representation, and this is extremely helpful for executing these types of activities. And it'll even pull information regarding mechanical integrity, which can be related to a software such as APM for a clear picture or visualization of all of the data pertaining to that particular asset.